All right, let's get right into it. If you're taking a calculus course, you've definitely met the derivative. You've probably spent hours memorizing all the rules, the power rule, product rule, you name it. But today, we're going to go beyond just the formulas and really get to the heart of what a derivative actually is.
So let's kick things off with the big question here. I'm sure you can find the derivative of x squared in your sleep, right? But what does that little apostrophe, that prime symbol, really mean? What is f prime of x telling us? Because it's so much more than just an answer for your homework. It's a peek into the language of how things change.
You see, to truly understand it, you have to realize the derivative isn't just one thing. It's actually got these three distinct but totally interconnected layers of meaning. So let's peel them back, one by one.
Okay, first up, the geometric view. At its most basic level, the derivative is all about slope. I want you to picture you're on a roller coaster, and the track is the graph of a function. The derivative at any given point tells you the exact steepness of the track right under your seat at that single tiny instant. So, if the derivative is positive, you're climbing. If it's negative, well, you're heading down.
The second layer, it's all about speed. The derivative is the function's instantaneous rate of change. Think about it like this. When you're driving a car, your average speed over a whole trip is one thing, but your speedometer tells you your speed right now at this exact second. That's precisely what the derivative does. It captures that rate of change in a single, fleeting moment. And this is where it gets really practical, especially in physics. If you have an equation that describes where an object is over a period of time, the derivative of that function isn't just some abstract number, it's the object's actual velocity. This is how we use math to describe the real-world physics of motion. It's pretty cool.
Okay, so that's the theory. But honestly, the best way to make these ideas stick is to see them all work together. So let's take a classic calculus problem, a particle moving through space, and see how these three ideas all come together to tell us a story.
So here's our scenario. We've got this function, s of t, and it tells us a particle's exact position at any time t. Our job, our mission, is to find its velocity. Not its average velocity, but its instantaneous velocity, right at the 4-second mark.
Now, I know what you're thinking. There are shortcuts for this, and you're right. But to really see where velocity comes from, we're going to build this thing from the ground up, using the formal limit definition of the derivative. This is like looking under the hood of calculus.
We're going to follow a simple 4-step game plan. First, we'll set up the big limit definition. Then, we'll dive into the algebra, expanding and simplifying everything. After that, we'll finally evaluate the limit to get our velocity function, and last but not least, we'll plug in our time to get the answer. Let's do it.
Okay, step 1. Now, this formula can look a little scary, but it's really just the good old slope formula, rise over run. The numerator, that whole top part, is just the change in position, and the denominator, h, is the change in time. The real magic is that lim part. By letting h get closer and closer to 0, we're basically finding the slope between 2 points that are becoming infinitely close, and that's how an average slope transforms into an instantaneous one.
And now, the algebra. Once you expand all those terms from the previous step, it looks like an absolute mess. But then, something kind of beautiful happens. The original terms, the t cubed and the negative 6t squared, they cancel out completely, leaving us with just this. And notice something really important. Every single term left has at least one h in it. That's the whole goal, because the h on the bottom is our problem, and if we can cancel it out, we're in the clear.
And boom! Once we factor out an h from the top and cancel it with the h on the bottom, we can finally let h go to 0. All those other terms with an h just vanish. And what we're left with is amazing. It's a brand new function v of t, which is our derivative. This thing is our particle's personal speedometer. It can tell us the velocity at any moment in time we want.
So, we have our velocity function. We did the hard work. Now it's time for the payoff. We're going to plug in our time, t equals 4, and see what this particle is actually doing at that specific moment. This is where the numbers turn into a real story.
0. After all of that algebra, the answer is 0 meters per second. But hold on, the number itself isn't the end of the story. The real aha moment comes from asking, what does that mean? What is a particle doing when its velocity is 0?
And this is where it all clicks into place. The calculation, v of 4 equals 0, has a powerful interpretation that connects right back to those first two ideas we talked about. From a physics point of view, a velocity of 0 means the particle has stopped, it's not moving. And from a geometric point of view, A slope of 0 means the graph of its position is perfectly flat, perfectly horizontal at that one instant. The math and the concepts are telling us the exact same thing.
The source material really just says it perfectly. The particle has momentarily stopped moving at t equals 4. It isn't moving forwards. It isn't moving backwards. For that one single instant in time, it's just still.
But that brings us to one last really interesting question to think about. Just because the particle stopped for a moment, does that tell us everything? I mean, it was moving before, and it's probably going to move again. So at that exact instant it was stopped, was it in the middle of turning around? Was it about to speed up? Or was it slowing down? Well, to answer that, we'd have to look at the next derivative, a little something called acceleration. But that's a story for another time.